items. First is the stimulus. Stimulus is a change in the internal or external environment that evokes a response. And our survival depends on sensation and perception of these stimuli. And so there's a difference between sensation and perception. Sensation is our awareness of the stimuli, the awareness of those changes that are going on in the internal and external environments. This is going to occur in the brain, same as perception is going to occur in the brain. But sensation is sort of just becoming aware of a stimulus. So say that I had a rock in my shoe, and that rock would create a sensation of localized pressure. And so I start to sense that there's this localized pressure going on in my foot. But I don't understand what that is unless there's also perception. And perception is going to be our conscious interpretation of those stimuli. What is the meaning of that particular stimulus? And so the fact that localized pressure is due to a rock, and it's a rock causing that localized pressure, is going to change how I actually react to it. So perception in turn determines how we respond to the stimulus. This also occurs in the brain as well. So sensation and perception take place in the brain, therefore input must be sent to the brain for sensation and perception to occur. So when we think about the primary motor or the primary sensory cortex, that primary sensory cortex is where sensation is taking place. We're becoming consciously aware of it. There's a lot of association areas that are going to be involved more with that perception aspect of things. But again, all that information has to get to the brain. And so this requires something called transduction. Transduction is the conversion of the energy of the stimulus into an electrical event. An electrical event that we're talking about here is an action potential. So in other words, a stimulus, that change in the internal or external environment, must excite some sort of receptor that's going to therefore create an action potential that can be sent back to the brain, where then sensation and perception takes place. And there's lots of different ways to classify different sensory receptors. Sensory receptors are specialized to respond to changes in the environment, and again, those changes are the stimuli, and we can classify our sensory receptors a number of different ways. First, we can do it based on what type of stimulus activates the receptor. We can have mechanoreceptors. Mechanoreceptors are going to be actually physically deformed when they actually get excited, and so they're going to be deformed by some sort of mechanical force. So vibration, pressure, touch, stretch, all these can excite in the mechanoreceptor. We have thermoreceptors. Thermoreceptors respond to changes in temperature. Photoreceptors respond to light energy. We know our photoreceptors are our rods and cones in the retina of our eye. We have chemoreceptors. Chemoreceptors respond to chemicals, and those chemicals must be in an aqueous solution. So we have to dissolve those chemicals first in an aqueous solution so that they can activate those chemoreceptors. Things like smell, taste, a lot of blood chemistry, all are going to be dependent on chemoreceptors. And then we have nociceptors. Noci means harm, and nociceptors are going to respond to potentially damaging stimuli by activating an action potential. When these are activated, typically you're going to feel pain. So things like excessive heat or excessive cold can activate things like nociceptors. We can also classify based on where the receptor is located or where that activating stimulus is located. And so we can have exteroreceptors, interoreceptors, and proprioceptors. Exteroreceptors respond to stimuli outside the body. So if they're going to respond to stimuli outside the body, they're going to have to be found at or near the surface of the body so that they can respond to those stimuli at those locations. Interoreceptors are also known as visceroreceptors. They respond to stimuli within the body. And so they find a lot of these interoreceptors in the viscera of the body, a lot in blood vessels, and typically if the interoreceptors are activated, you're not typically aware of their activation. You may experience maybe some discomfort, some pain, maybe thirst, but for the most part those interoreceptors are activated to give information to the brain about what's going on with the internal organs, but you're not typically aware of what's going on. We also then have a special type of interoreceptors known as proprioceptors. And these are interoreceptors because they're found internal in the body. So they're specialized interoreceptors, but they respond to this internal stimuli only in certain locations. These proprioceptors are found in skeletal muscle, tendons, joints, and ligaments. And so they advise the brain about body movements. You always have that feedback going back to the brain, especially to the cerebellum, so that you know what movements are going on. If I close my eyes and I move my upper limb, the fact that it's moving, I know that without seeing it, and it's because of those proprioceptors. They're allowing my brain to know that those movements are going on. We also can classify our sensory receptors based on how complex they are. Simple receptors are most of what we have in the body. These are just basically modified dendritic endings of the sensory neurons. So we talked about that information coming in from the skin. A lot of the receptors coming in, bringing in or being activated at the surface are actually just modified dendritic endings. And so those are involved with simple general sensation. Touch, for example. So vibration, temperature, those are a lot of simple receptors. We also have complex receptors, and complex receptors are also known as special sense organs. And when you look at these complex receptors, those complex receptors are going to have a collection of different types of cells. Some of those cells are the receptor cells, but you have other cells there in a supportive role. So complex receptors, which are known as the sense organs or special sense organs, are collections of different types of cells. Some of those cells do the transduction for you, but other cells don't. But these complex receptors are involved with special sensation. So we're going to look at special sensation. In special sensation, there are 5 special senses in the body: taste, smell, sight, hearing, and equilibrium. Touch is not listed here because touch is going to be a general sensation. So touch is a general sensation. Well, if we're talking about the special senses, what we're interested in are these complex receptors. So the 5 special senses are going to require complex sensory receptor organs, which contain receptor cells and other supportive cells as well. And we're going to first start with taste or gustation. When we look at taste or gustation, and a lot of this should sound somewhat familiar, I hope. The receptors here are going to be chemoreceptors. So that means that the chemicals for taste, which are called tastins, have to dissolve in something, and what they're going to dissolve in is going to be saliva, so that they can activate the chemoreceptors. Those chemoreceptors are found in the taste buds, and we've talked a little bit about this before. So this is going to be the complex receptor. So we're going to have our actual chemoreceptors plus other supportive cells there. And remember, taste buds are found predominantly on the tongue and associated with fungiform and circumvallate papillae. Hopefully a lot of people remember that. But they can also be found on the taste buds can also be found individually on the soft palate, part of the pharynx, the epiglottis, and the surface of the cheeks. Humans have approximately 10,000 taste buds. And so remember that when we go looking for the taste buds, we can find the taste buds in a number of different locations, but as an adult we find taste buds associated with the certain papillae, the fungiform papillae as well as the circumvallate papillae. And here they pull the circumvallate papillae out, we look at the lateral border of the circumvallate papillae, and that's where we find the taste bud. And here's the taste bud in cartoon representation, and here it is in histological section. And when we look at that taste bud, we can see there's lots of different cells, actually 3 different types of cells associated with it. We're going to have associated with it the gustatory cell, also known as the taste cell. That gustatory cell or taste cell is going to be the chemoreceptor, that cell which is going to be able to do the transduction for you. So we see that what happens is the tasting comes in, it's going to dissolve in the saliva. It's going to bind to the long microvillus that comes out of this gustatory taste cell and out of the taste pore. And it's going to cause certain channels to open and close when it binds. And wrapped around the base of these gustatory cells is the beginning of the pathway back to the brain. So we have to get back to the brain so we become consciously aware of what's going on in terms of taste. But there's other cells there that are in a supportive role. Here's the supporting cells here. And then again, these are in a very vulnerable location, and so very often taste buds are going to be damaged. And so we have along the base of here, the basal cells that can replace both the supporting cells and the gustatory receptor cells. Well, if we have the beginning of the pathway back to the brain wrapped around the base of those cells, where is that information going and how does it get there? So special sensation for the tongue is supplied differently depending on where you are. If you're dealing with a taste bud on the anterior 2/3 of the tongue, so we're looking at the anterior 2/3 of the tongue, so we know that we go to the sulcus terminalis, which is this area here, go to the circumvallate papillae, and we're looking at the circumvallate papillae and anterior to that point. That's the anterior 2/3 of the tongue. Wrapped around the base of those gustatory receptor cells is the beginning of the pathway back to the brain. If it's on the anterior 2/3 of the tongue, what's wrapped around there is the chorda tympani nerve fibers from the facial nerve. So the facial nerve is doing taste to the anterior 2/3 of the tongue. Now the interesting thing is, although taste is done to the anterior 2/3 of the tongue by the facial nerve, specifically the chorda tympani nerve from the facial nerve, general sensation is actually done by the lingual nerve, which is a branch of the mandibular division of the trigeminal. So trigeminal, 5, does general sensation, while special sensation is done by 7. So if I take a piece of candy and put it on the tip of my tongue, the fact that that's sitting there, that pressure, that is information is sent back to the brain by 5. But the fact that it's sweet is sent back by 7. These two are going from the same area, so they run together, but they're different fibers from different nerves. Okay? That makes sense?
Can you say that one more time?
So if you put a piece of candy on the tip of your tongue, the fact that it's sitting there, that pressure, that's going to be from 5. So it's coming from the lingual nerve, which is a branch of the mandibular division of the trigeminal. But the fact that it's sweet, that information gets back to the brain through the chorda tympani nerve, which is a branch of 7. So touch is going to be 5, taste is going to be 7. They're running together as they're coming from the same area, but certain fibers are from 7 and certain fibers are from 5. Yeah.
So does the hypoglossal not have anything to do with any of the sensations?
No, it does not. It's going to be hypoglossal nerve is going to be dealing with movement of the tongue, so skeletal muscle. Yeah. Posterior 1/3 of the tongue, so behind all of these circumvallate papillae, and a little bit of the pharynx. So we're going to see that that area is from both general and special sensation by the lingual branch of the glossopharyngeal nerve. So 9 is going to get both general sensation, so touch, as well as the fact that it's sweet, is going to be from 9. So certain fibers of 9 carry information that it's sweet, other certain fibers of 9 carry the fact that it's general sensation. Now if we head back to the epiglottis and the lower portion of the pharynx, there's still taste buds back in that area. Both the general sensation and the information from the taste buds from the internal laryngeal nerve from the vagus, 10. So it's also getting general sensation to that area. So you may see some images that show the tongue and show general sensation. If it's general sensation, it would be 5, 9, and 10. But if it's going to be special sensation, it's going to be 7, 9, and 10. So here they're showing you the information coming back to the brain. And so here's the anterior 2/3 of the tongue, and so this is the chorda tympani nerve, a branch of the facial. Back here, this is the posterior 1/3 of the tongue, and so this is branches of the glossopharyngeal. And here's the vagus coming from the epiglottis. This is all coming from special sensation, so this is coming from the bottom of the taste buds, from those receptor cells. That information, you're still not even aware of it, is gonna come up, it's gonna have a nice synapse over in the medulla oblongata, it's gonna switch sides, it goes up to the thalamus, because most sensory information goes to the thalamus for a nice synapse or two. We have a synapse there, and then we're gonna go to the primary gustatory cortex. The precise location of the primary gustatory cortex is a little bit in debate, but they know it's right here. It's gonna be at the bottom of the parietal lobe and a little bit in the insular lobe, right in this area right here. And that primary gustatory area is where you become consciously aware of taste. Now, understanding it is gonna be related to association areas, but this is where you become consciously aware of it, when this is activated here. What artery serves that area?
Middle cerebral.
Middle cerebral. So if you have a problem with your middle cerebral artery, you may have a problem with taste on the contralateral side of the body. Any questions on taste or gustation? Now, the interesting thing about taste is also overlaps with smell. And so taste is about 80% smell. So what you perceive as taste is about 80% smell. That's why if you have a cold and your nose is plugged up, you don't taste as well. Everything kind of has a dull taste associated with it. So there's a nice crossover between taste and smell. And that's what we're gonna talk about next. Next, we're gonna talk about the olfaction sense. Again, our receptors are chemoreceptors. So what we are going to breathe into our nose, remember, are called odorants. And so those chemicals, those odorants come into the nose, and we have to breathe in really deeply if we want to get even more odorants up to that area, because remember, our complex receptor is the olfactory epithelium. So that olfactory epithelium is gonna have those chemoreceptors, plus some other supporting cells. And that olfactory epithelium is in the roof of the nasal cavity, along a little bit of the superior nasal concha, and the superior portion of the nasal septum. So it's way up inside the nasal cavity, so if you want to smell something really well, you take a deep breath in so you can get those odorants up into that area. Those odorants are going to dissolve in the mucus that is produced by the cells of the mucosa. So what they've done here is they've shown you, this is the lateral wall of the nasal cavity, and they've shown you the superior nasal concha here, and there's the roof of the nasal cavity, and this is that olfactory epithelium. They brought it over here, so here's the olfactory epithelium, here's your cribriform plate of the ethmoid, and sitting on, remember, on the cribriform plate is going to be the olfactory bulb. So we're interested first in this here. This is going to be the olfactory epithelium. And that olfactory epithelium has a number of cells associated with it. Included in there are going to be the olfactory receptor cells. It is these olfactory receptor cells that are the chemoreceptors. They're the ones that are going to do the transduction for us. And you can see that they are bipolar neurons. So one end is going to come out towards the surface. This is the dendrite. And once it gets to the surface of the mucosa and in the mucus, it's going to send out extension, so it has a lot of surface area associated with it. We call that the olfactory cilia. So if you breathe in, those odorants are going to dissolve in the mucus. We are then going to have them bind to those olfactory cilia. It causes a chemical change in these cells. The ions are going to change up a little bit, and that information is going to come back and it's going to get to the axon hillock, and where we initiate an action potential, and an action potential goes along the axons of these olfactory receptor cells. It is the axons of these olfactory receptor cells that are cranial nerve number 1. So cranial nerve number 1 is the axons of these olfactory receptor cells. Now remember, this is a complex receptor, so they're not the only cells there. We also have supporting cells that are there. We also have basal cells that can produce our supporting cells and our olfactory receptor cells when there's some sort of damage. So we smell something, comes in, It's gonna dissolve in the saliva, or not in the saliva, in the mucus. It's gonna bind to the olfactory cilia. We get an action potential, and it's sent along cranial nerve number 1. It goes through the cribriform foramina of the cribriform plate and comes into the olfactory bulb. Cranial nerve 1 then is going to synapse with these what are called mitral cells, and these mitral cells then send their axons back as the olfactory tract back to the brain. So cranial nerve number 1 is just the axons of these olfactory receptor cells, not the olfactory tract. The olfactory tract is the axons of these mitral cells. The axons of these mitral cells. Now what you actually saw on the brain was the olfactory bulb and the olfactory tract. You can't see if you're holding the brain, cranial nerve number 1, because it got left behind in the skull. So when you pop the brain out, the tract and the bulb goes with it, but it leaves these axons back in the skull, which are cranial nerve number 1. Here, here, and here, and a couple more. Okay. So the question is, where is this information heading? Well, first we want to be consciously aware of it. So we want to go to the primary olfactory cortex. And so we're going to go to the primary olfactory cortex, which is mostly located in the medial aspect of the temporal lobe. It's where we receive impulses for smell and is followed with olfactory sensations, where you become consciously aware of it. When I say medial aspect of the temporal lobe, what do I mean? I found a picture this morning. So if you look at this particular picture here, this is a sagittal section of the brain. Here's the temporal lobe. We're looking right at this area right in here. This is the primary olfactory cortex. Now the interesting thing was, as we headed to the primary olfactory cortex, we did not go to the thalamus. It turns out that this is the only, olfaction is the only sensation that's not relayed through the thalamus. So there's an exception there. Now if we're looking at this medial aspect of the temporal lobe, who do you think serves this? What artery is going to supply this area right here?
Is it middle cerebral?
It's middle cerebral again. So if you have a problem with middle cerebral, you may also have a problem with smell. So we get that information to the medial aspect of the temporal lobe, which is served by the middle cerebral. We start to become consciously aware of it. But we want to understand what that smell is. We want to tie it to previous experiences. So we have connections from that primary olfactory cortex to the occipital frontal cortex for identification and discrimination of the odor. So we actually add that perception to it. But there's an interesting part about where these impulses are going to. We're not only sending information to the primary olfactory cortex, but we're also going to take a subcortical route to areas of the hypothalamus, amygdala, and other portions of the limbic system. Remember, the limbic system is going to be where it's sort of our emotional area. It's also where a lot of memory takes place. It's a functional area that includes different parts of the brain. And we're sending information there for both emotional and memory invoked responses. And if you've ever gone house hunting, a lot of realtors will play against this. So a lot of times if you walk into a house, they've just baked cookies, if they have an open house, and so you start smelling those cookies. And so you become consciously aware of that smell, you start to discriminate it, but you also send it to that subcortical root, and you start to remember, oh, I remember when Grandma made those cookies, and I remember Christmas, and I remember the holidays, and oh, it was so wonderful, and oh, I want this house. Because it reminds me of Grandma.
That's
And
a real
so-
tactic? They really do that?
Mhm. It starts playing on your memories and invoking those memory responses. And so it starts really playing on that, and so that's what the realtors are playing on. But at the same time, it's also a defense mechanism. Say you walked into that house and smelled natural gas. That's also gonna kick in that subcortical root, and so it's going to trigger that fight or flight system. Oh, I gotta get out of here, this is dangerous, I gotta leave this area. So really, that subcortical root is actually a defense mechanism. It also turns out appetizing odors, also going through this route, are gonna stimulate the parasympathetic system to stimulate the digestive tract and increase salivation as well. So there's a lot of sort of side things that happen when you're smelling things. You become consciously aware of it, you perceive it, but other things start to happen, especially with the autonomic nervous system. Questions? So let's look at sight. So in sight, we're looking at our complex receptor, so we have a lot of cells there that are making up what's called the eyeball. And in that eyeball, there's lots of different cell populations, including our photoreceptors, which are the receptors that are going to be activated by light. So when we look at the eyeball is composed of 3 coats or tunics, and the eyeball itself is going to be a slightly irregular hollow sphere. We have the 3 coats or tunics. On the outer portion is the fibrous tunic. We go deep to that, we're going to have the vascular tunic, and deep to that we have the sensory tunic. We also have, as it's a hollow sphere, some cavities or spaces which are filled with what are called humors. 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 And humors are the liquids which we find in the internal cavities. We'll talk more about those. And in those internal cavities, we also have a lens. And the lens is the adjustable focusing part of the eye that lies within that internal cavity. Well, let's go through the 3 tunics or 3 coats. And we're going to start with the outermost coat of the eyeball, and that's going to be the fibrous tunic. And that fibrous tunic is composed of avascular connective tissue, so no blood vessels. It's avascular connective tissue. The posterior 5/6 of the eyeball, so here's our eyeball here, and the posterior 5/6 of it is going to have on the outside something called the sclera. The anterior 1/6 is going to have the cornea. So the sclera and the cornea are going to make up this fibrous tunic, this outer portion of the eyeball. So that sclera makes up the posterior 5/6 of the fibrous tunic. The sclera is white and opaque. It's the white of your eyes. It protects and shapes the eyeball. And very importantly, it also provides an insertion point for the 6 extrinsic eye muscles. So it's going to provide an insertion point for your 6 extrinsic eye muscles that allow you, they're skeletal muscles that allow you to move the eyeball around and look at different things in your environment. Then you have the cornea making up the anterior 1/6 of the eyeball. This cornea is going to bulge anteriorly. It's transparent. And it's the first structure of the eye that light passes through. So it's the first structure of the eye that light passes through. So if you want light to come into the eyeball, it's going to have to come first through the cornea. So it makes sense that this layer is avascular because you wouldn't want any blood vessels in there to refract the light. But because the cornea is bent, it is curved, it does bend the light. So light is first bent as it comes into the eyeball from the cornea. We're going to go a little deeper now, and so we're going to go to the vascular tunic. And the vascular tunic is shown here in the red. The vascular tunic is going to have different parts associated with it. We're going to have the choroid layer, which makes up the posterior 5/6 of it. So we're going to have the choroid layer, makes up the posterior 5/6. Anterior to that, we're going to have the ciliary body, and then the iris. Ciliary bodies, and then the iris. First talk about the choroid portion. choroid portion, it has lots of blood vessels associated with it. And it also contains brown pigment, so that choroid layer also contains brown pigment to help absorb light, preventing it from scattering within the eye, causing visual confusion. So lots of brown pigment in that choroid layer, along with blood vessels. We also have the ciliary body, anterior to the choroid, and it encircles the lens. So think about the fact that this is a two-dimensional image here. You've got to think about this as being three-dimensional. Here's your lens, and this is going to be that ciliary body, and it's going to encircle the lens. So this completely encircles the lens, goes around it. The ciliary body is going to have different parts associated with it. First are the suspensory ligaments or zonular fibers. The suspensory ligaments or zonular fibers. That's going to be these structures here. And again, they completely encircle the lens. Completely encircle the lens. These suspensory ligaments encircle the lens, connecting the lens to the ciliary bodies. These ligaments help to maintain the lens position and also allows the ciliary body to pull on the lens, changing its shape. Because also in the ciliary body are ciliary muscles, and these are smooth muscles. These are smooth muscles. And those smooth muscles are going to be able to contract and relax, pulling on those suspensory ligaments and therefore changing the shape of the lens. So focusing light differently onto the retina. Also in the ciliary body is what's called the ciliary processes. Ciliary processes contain capillaries that secrete one of our humors known as aqueous humor. So the ciliary processes are usually back here in this, a little bit in this area right here, lots of capillaries there. And there's going to secrete something called aqueous humor, which is one of the two humors we have associated with the eyeball. We'll talk more about that in a few minutes. We then have the iris, this portion here. And again, remember this is a two-dimensional image of something that's actually three-dimensional. So it's going to come out and circle around. This is the colored part of the eye. Interestingly, though, it contains only brown pigment. So how that brown pigment is organized, how much of that brown pigment you have is going to create different eye colors. In the middle of the iris is a central opening known as the pupil. And this is what light is going to pass through. So that iris is going to contain smooth muscle. And that smooth muscle in the iris, and here we are looking at the iris, and we're looking at that smooth muscle, is arranged in two patterns. So this is another place we have smooth muscle. We have a smooth muscle in the ciliary body, we have the smooth muscle now in the iris. And so we can see that smooth muscle either in a circular pattern or in a radial pattern. So either circular pattern or radial pattern. The circular layer of smooth muscle, when it contracts, it's going to close down or constrict the pupil. Okay? So that lets less light in. That circular layer is under the control of the parasympathetic division, the autonomic nervous system, which is your rest or digestive system, which kind of makes sense because if you're doing your normal everyday activities, you want to protect the retina and just let a little bit of light in so you can do your everyday activities. Well, there's also the radial layer. And when these smooth muscles contract, it causes the eye to dilate, to open up, let a lot more light in. And it does so in dim light situations. Also, if you want to do distant vision, you want to let as much light in as possible. So this is distant vision, dim light situations. This is going to be when you're reading something, so something up close, or we're going to protect the retina because you're in a bright light situation. Interestingly, though, a lot of this smooth muscle, besides being controlled by the autonomic nervous system, there's a lot of ties between the autonomic nervous system and emotions. And so emotions and interests can also impact what's going on with this smooth muscle. If you're dealing with something that's boring or repulsive subject matter, the circular layer is going to constrict. So we see that circular layer is going to constrict, and so it's going to close down. If you're dealing with something repulsive or boring, I don't want to deal with it, I want to not let as much light in about it, I'm going to close it down. If you're dealing with the appealing subject matter, if you're problem solving, you want as much information in as possible. If something's appealing, I want to see it as much as possible. And so the radial layer is going to contract, and it's going to dilate the pupil. So if you're on a first date and you're not sure how it's going, if you look into your date's eyes and you see this, things are not going so well. If you see this, there probably is going to be a second date. Going to the last layer, that's going to be the sensory tunic or retina. This is the innermost layer, but it only lines the posterior 3/4 of the eyeball. It doesn't go all the way around to the front, so it's only going to line the posterior 3/4 of the eyeball. And what we see is that this is the only layer playing a direct role in vision. This is the only layer playing a direct role in vision. It's actually interesting, this layer is actually developed from an outpocketing of the brain during embryonic development. So the brain is actually going to send out these out pockets. It hits the surface and then it bounces back and creates this cup of the retina. So it's kind of interesting. It's actually formed from the outpocketing of the brain. When we look at the retina, there's different cell populations there, and they're very organized into layers. We're going to have outermost the photoreceptor cells, which are our rods and cones, and those photoreceptor cells are the ones that are going to respond to the light. These are the ones that are the receptor cells. They're the ones responsible for the transduction, taking the energy of the stimulus, converting it to the action potential. Then you're going to have bipolar cells, and bipolar cells are responsible for spreading that signal that was developed by the photoreceptor cells. So the photoreceptor cells start the signal, send it to the bipolar cells, and the bipolar cells are going to send it to the ganglion cells. The ganglion cells are the innermost layer of these three cell populations, and the ganglion cells' axons are going to leave the back of the eyeball as cranial nerve number 2. So it's the axons of these cells, these ganglion cells, that make up cranial nerve number 2. So we're looking at the retina, also known as the sensory tunic. It's only going to cover the posterior 3/4 of the eyeball, so it's only going to go around to about this layer here. It doesn't come up to all the way to the front. It doesn't come through here. And here you can see the eyeball. This is where light is going to come in, and it's going to come in and it's going to hit that sensory tunic. So we're going to go into the sensory tunic. But the interesting thing is the first layer of cells are your ganglion cells. They don't notice the light. Then we get to the bipolar cells. They don't notice the light. It's got to go all the way to the outermost portions of the retina, to the rods and the cones, so that transduction can take place. The transduction takes place here, then our electrical signal is sent to the bipolar cells, to the ganglion cells, and then our ganglion cells send their axons back as cranial nerve number 2. It's kind of weird how it's set up. So light is actually going to have to go through all of these layers to get back to the rods and cones. We have transduction take place here, and our signal goes back the other direction to the ganglion cells. So signal is going to come back, our light's going to come back. It's going to go past the ganglion cells, past the bipolar cells, to the rods and cones. Transduction takes place. Our signal goes to the bipolar cells, to the ganglion cells. Our ganglion cells send their axons back as cranial nerve number 2 towards the brain. Well, also associated with the eyeball are going to be chambers. And we see those internal chambers have fluids associated with them. And so we see there are 2 fluids. And so we have these internal chambers divided by the lens and the suspensory ligaments into our anterior segment and our posterior segment. So we have all this internal chamber area, and then we have an anterior segment and a posterior segment divided by the lens and the ciliary body. If we're looking in the anterior segment up in this area here, what's in this space is something called aqueous humor. I mentioned that before. Aqueous humor. Aqueous humor is produced constantly throughout your lifetime. It's produced by the capillaries of the ciliary body, specifically the ciliary processes. We then are going to have that aqueous humor flow through the pupil up into the front. You can see this junction right here, this junction between the sclera and the cornea. There's a little opening right there called a canal of Schlemm, and that's where it's reabsorbed. It's sort of like cerebrospinal fluid. You produce it from blood plasma. You shouldn't have any red blood cells associated with it. You produce it from the plasma, you reabsorb it into the blood. So you make it from blood, you're gonna reabsorb it into the blood. So it's gonna flow through here, and back into there, flow through here, and back into there. So aqueous humor is constantly produced throughout your lifetime, and that aqueous humor does a number of things like transmitting the light, contribute to intraocular pressure, supplies oxygen and nutrients, gets rid of waste products, because remember, the cornea doesn't have any blood vessels, so somehow those cells there have to get what they need, and so they're gonna get it from this aqueous humor that's flowing through this area. We then have the posterior segment, which is going to be found posterior to the lens, and it's filled with what's called vitreous humor. And vitreous humor is sort of like gel. It's very gel-like. It's like a clear gel. It forms in the embryo and lasts for a lifetime. So what you're born with is what you're going to have throughout your lifetime. That is also going to transmit light. It also contributes to intraocular pressure. And it holds the neuronal portion up against the pigmented layer, which is important because our rods and cones actually get their blood supply from that pigmented layer. And so if you ever heard of a detached retina, it's when the retina pulls away from the choroid layer, and so it loses its blood supply. So normally those two should be up against each other. Also, vitreous humor helps to give the shape to the eyeball.
You said a detached retina is when the retina detaches from the choroid layer?
Mm-hmm. So normally the rods and cones are going to get the blood supply from that choroid layer. So if you split those two apart, you get that's the detached retina. It's actually going to cause the rods and cones to die if they're not reattached. Okay. Then we have the lens. Don't forget about that. This is biconvex, so it's angled or bent on both sides, biconvex, transparent and flexible, and it can change shape, which is important because that allows for precise focusing of the light onto the retina. Light is going to come in, and when it comes into the lens, it's going to be bent or refracted on both sides. So we already saw our light was partially bent when it came in from the cornea, but it's also then going to be bent when it goes through the front side of the lens and the back side of the lens. And because the light is bent as it goes through the eye, what we're going to see is that we have what's called the real image, which is focused onto the retina, which is upside down and reversed right to left or left to right. So, for example, if you see this orange block up here on the top, on the right-hand side, you can see now it's on the bottom on the left-hand side. And this is the real image. Your brain has to flip it back to its original shape, original location, and the brain is going to have to do that. So what is actually displayed onto the retina is upside down and reversed right to left, and that's called the real image. Your brain is going to have to flip that back for you. So the next couple slides just kind of go through each of the areas and lets you, reminds you of the different parts of it and the different functions. So it's a nice little summary of the fibrous tunic, the vascular tunic, the retina and the lens. Then we saw the different chambers or cavities associated with aqueous humor and vitreous humor. And a lot of people at this point ask me some questions related to the fact that when we look at somebody's eyeball, we actually see a lot of blood vessels associated with it. And that's kind of odd when we talk about the fact that that outer layer of the eye doesn't have blood vessels associated with it. So when you look at the sclera, by itself, it doesn't have any blood vessels associated with it, but if you look at somebody's eye, look at the white of somebody's eye, you see blood vessels along the surface. And that's because of the conjunctiva, which is not part of the eye. I did not mention it because it's not part of the eye. It's a partial covering over it. It's a very thin protective membrane, and we can see that there's different parts to the conjunctiva. So if we follow the skin, here's the skin coming down. We then go on the inside of the eyelid, and this is the beginning of the conjunctiva here. And then it's gonna turn and then go along the surface of the eye. But it only is gonna go so far, and it does not cover the cornea. So when you look at the white of somebody's eyes, you see blood vessels. Those blood vessels are part of the conjunctiva. But the conjunctiva will not cover, or should not cover, the cornea, because you do not want blood vessels interfering with light passing through the eye. Some other structures I did not mention, the lacrimal gland, which you can see here. You have this on both sides. The lacrimal gland is going to produce fluid known as lacrimal fluid, which is also known as tears. It's about the size and shape of an almond, found laterally and superior to the eye. And that fluid is very important because every time you blink, that fluid is going to come out and it's going to cross the eye. And it's serving a protective measure as it can get rid of any debris along the surface. And you produce about 1 milliliter of lacrimal fluid per day. Again, it spreads over the eye, provides protection as the tears dilute and wash away any irritating substances. And we see that that fluid's gonna go somewhere, and so it's gonna head over here medially. And remember, medially is the nasolacrimal duct. So it gets into the nasolacrimal duct, which then goes down to right behind the inferior nasal concha, and then brings that fluid with any debris into the nose. That's a good spot to stop for today, because I think it's gonna be a little rushed if I try to go through the vision pathway today. So why don't we stop there, come back to this tomorrow, and then we'll start the next lecture